So is HCl soluble? Yeah, aqueous. Is sodium hydroxide soluble? Sodium hydroxide soluble in water?
Sodium salt.
Yeah. Is sodium chloride soluble?
Yes.
Yes.
Is water soluble? Yes, water dissolves in water.
Oh, but that's water. Water is that's
You put it as H2O again? Or what is
Well,
the
no.
difference of it?
Basically, this is it. There's a reaction curve. If you take a strong acid HCl and react it with sodium hydroxide, what you form? You form salt water. I remember this equation very well because I remember high school chemistry. My high school chemistry teacher said, if you take a strong acid like HCl and mix it with sodium hydroxide, you'll form salt water, and you can drink the salt water. So all semester long, I was waiting for him to drink the salt water, but he never did.
Yeah, we're waiting for
He
you to
never
tell the budget
trusted his
also.
own technique. I don't trust my, you know,
What happens if there's like a long?
I might trust my technique, but I might not trust who made this hydrochloric acid and who made the sodium hydroxide. You know, you're putting your faith that they made it correctly, but maybe they're not so careful. No, I would adjust the pH.
Just dilute it.
You know, if I did this reaction, I'd just check the pH. If the pH came out, sodium chloride's neutral. Sodium ions are neutral, chloride ions are neutral, so it should come out to about pH 7, and then I'd drink it. So I would do that, but you don't know. You don't know if a jar of chemicals sitting in the lab, you don't know who touched it. You don't know what they put in it. You don't know if they care about contamination or what. You know, they might have dipped something in, let's say, lead, and then accidentally mixed. Have you ever? I don't know if you guys have the error, but I was in the error where, like the Reese's peanut butter cup. You know, that you got peanut butter on my chocolate. No, you got. Have you ever seen that commercial? Yeah, it's the same thing. Some people really are they don't care, and I'll tell you when I realized this. I realized this when I had my coffee mug in lab. I had my coffee mug in lab, and somebody said, "Oh, you know, that would make a great holder for my thallium samples." And thallium is, you know what the history of thallium is? Thallium is one of those chemicals that were used in like the Victorian era for murder. You know? Yeah, it was for murder. And so I was thinking, are you trying to murder me? So
He was giving you a hint to.
yeah, hint. Right.
Giving you some
But you
time.
know, the person said, "What's the big deal? Why are you so upset?" You know. So I told the person, "I'm going to throw away my mug," and they said, "You're crazy. It's just a little thallium's not going." And then I realized, you know, chemical hygiene. There are people who have totally different ideas about chemical hygiene than you might. And you might think everybody's going to treat everything the same way as you do, but don't believe
You
it.
could have just watched them. You could just watch them.
I ended up washing it out.
With some alcohol.
And I kept the mug. It was my UCSB mug.
Were you ever nervous to drink that?
Huh? No, because I could clean it thoroughly. No. It's just if you didn't know, you know, if they dropped the samples in there and you don't know, and then you took it out, and then you start drinking it. My advisor had, my boss there at UCSB, he had some hair sample taken, and he had high levels of thallium in his hair. Yeah. Thallium's a heavy metal. So anyway, this is all soluble, but there's a reaction. What's the driving force for this reaction?
The liquid?
No.
No?
Stronger acid to
Oh,
weaker acid.
Water's the...
Right. You try to keep it simple. What you do is you don't try to memorize a whole bunch of different driving forces. You just try to memorize the basic driving force and then use that for everything. I know a lot of people will say liquid formation, but I can give you examples where liquid formation fails. You know, liquid formation works for certain things, yeah, for most things.
What would the NIE look like?
The NIE for this? The NIE looks like this. H plus plus OH minus yields H2O liquid. That's the NIE. This is an example of what type of reaction? Acid base or a metathesis. I classify this as metathesis, or acid base. But it's set up, the way I did this was as a metathesis. I didn't solve this as an acid base. When I do a Bronsted acid base, I follow a clear set of steps. As long as you follow that clear set of steps, then you should be able to get it. So what are the first steps? What are the steps okay, I told you that D is what type of reaction? Acid base. So what are the steps in acid base? Inventory. So the first thing I'm going to do is inventory. Well, sodium salt is soluble, so that's going to yield sodium ions and what's the anion here? Oxide. Sodium ions and oxide ions. And then I go over here, well, I get sodium ions again. I'm not going to write it over again because I already have that in the inventory. And then I'm going to have chloride and water. Water is actually the most abundant species usually in these reactions. It's the most abundant, but it's most often ignored. Why is it most often ignored? It's most often ignored because it's not so reactive. Is water a strong base? No. Is it a strong acid? No. So that's why it's ignored, but we can't always ignore it. So sodium ions, are those acidic, basic, or neutral? Neutral. Oxide.
Probably a little bit more to guess. A little bit of sodium.
It can be a strong base or weak acid.
Well, oxide can only be one of those.
Strong base.
Yeah. You should look at this chart once in a while. The reason you should look at the chart is just to familiarize yourself with it, not to memorize it.
How do I the idea if it's an acid base or neutral? Like, is it based off of the chart that you give us?
Yeah.
How do we know it's neutral?
Once in a while, you should look at the chart because something should stand out. Oxide is a very powerful base. And so the first thing I notice is I got a powerful base here. This is going to be reactive. And so oxide only occurs on the base side. It's not amphoteric. Chloride.
It's a base.
It's a base, but it's so weak. It's usually neutral. In fact, it's so neutral that sodium is neutral and chloride, even though it's a base, is so weak we call it neutral. So sodium chloride is basic or neutral. It's neutral. Table salt is going to give us a pH 7. And so it turns out that that base is so bad, this thing comes out pH 7.
I have a question.
Uh-huh.
If you have NH4, you don't break that up into NH, right? It stays as NH4.
Yeah.
And same thing with like cyanide, right?
Right. What's water?
Acid and base.
Water is an acid and base. So what's the next step?
Strong base and strong acid.
Pick the strongest base and strongest acid. What's the strongest base present? Oxide. What's the strongest acid present? Water. And so the reaction, if there is a reaction, because we don't know if there's a reaction, we have to see if there's a driving force, will be between water and oxide. Now what do acids do?
Acids,
They take a hydrogen or lose a hydrogen?
They lose a hydrogen.
Okay, so if water loses a H+, what's left? If water loses one of the H's, hydroxide's left. And if oxide gains that H+, what does it form?
O2 gas. Oh. But you said that the O.
Oh, yeah.
If oxide gains an H+,
Oh.
it forms. All right, then we do the driving force. This was our acid, this is our base. So the acid lost
Yeah.
a hydrogen,
Could either of those be the acid or base?
and so this one's going to be the base going backwards. This one will pick up a hydrogen to go back to water. This one is going to be the acid going backwards because this one loses the hydrogen going backwards.
So if you mark the other one acid and this one base, would that be wrong?
It wouldn't be
Depends on your
wrong.
train of thought.
It wouldn't be wrong. You just have to keep track of it. If you mark this one the acid, then it came from this. If you mark this one the base, then it came from that.
Okay.
That's the conjugate pair. Now we compare the two acids. What's a better acid, water or hydroxide? Water? What's a better base, oxide or hydroxide?
Oxide.
Oxide's a better base.
Okay. So there is driving.
There's a driving force.
How do we know that N is neutral?
Is it does it have a hydrogen to donate? Na plus doesn't want a hydrogen. Is this reaction favorable?
No. Funny thing that's.
Does that look reasonable to you? No. So it's neither. Acid nor
Has
base.
anybody ever tried to do that? Na plus hydrogen.
Yeah. All the time.
What happens?
Nothing. They stay away from each other. The one's positively charged, the other's positively charged. They stay away from each other. Light charges repel.
Are we gonna get the chart to finish the quiz? Or is that
You're going to get the chart to finish the quiz, but we're going to do the quiz at the end. So I just did this one for you. What you want to do is this. You don't want to think about these things too much. All you want to do is do it step by step and follow the steps. Like, for example, you don't want to think, if it's all soluble, then there's no reaction. No, just follow the steps. As long as you follow the steps, you should be all right. You don't have to know more. Once you're comfortable with all these, then you can start thinking about these patterns, but you're jumping too far ahead. You first look at the patterns and then figure it out. You don't figure out the patterns first and then look at the data. So for example, this chart on the left here, this chart on the left is intimidating because there's so much data. But what you do is you look at it, you don't memorize everything. It'd be great to memorize it, but you don't have to memorize it because, just rote memorization is not very effective or very useful. So what you're going to do is you're going to look for things. What are the things you look for? You want to be able to recognize the powerful oxidizers, and you want to be able to recognize the powerful reducers. That way, if you see similar substances, that might be a powerful oxidizer, a powerful reducer. Those are going to be the most reactive. Then you look, at certain patterns. Like we looked at one pattern yesterday. All the powerful reducers were what? Metals. Yeah. And in fact, the most powerful reducers were the alkali metals. That kind of stuff. And so that kind of stuff makes this chart a little easier to digest. What often happens is this. A lot of people say this is too much. They'll never look at it. If they never look at it, then number one, they're going to be slow when they use it. Number two, they're going to be confused when they use it.
I'm confused when I use it.
Yeah. And so what you do is you start using it and you start getting more and more comfortable, more familiar with it, and it gets better. But initially, it's too much. Initially it's too much, but we're going to be looking at this. So we have the two-pronged approach. The two-pronged approach is theoretical and experimental. This is from experimental data. What we want to do is we want to try to understand this chart more from a theoretical perspective, more from a structure and composition perspective, and that will give us more insight into it. Yeah.
What is better, theoretical or experimental? Or do they work together?
They work together. Most companies will have both. They'll have theoretical and experimental people. Like if you look at drug companies, they have teams of people on the theoretical side and teams of people on just the experimental side. So the experimental side are the types of people who go to like the rainforest and look for undiscovered compounds, that might show medicinal properties. The theoretical side, they're looking at the computer.
Combine everything, make it one.
Yeah. There's sometimes they're competitive. Like at the, sometimes they're a little competitive. a story about the blue LED. There's a race for who would discover the blue LED first, the theoreticians or the experimental people.
What is light? What's that?
The blue LED.
Light first.
Well, the red LED gives off red light, and that's been around for decades. The red LED. Red LED was discovered many years ago, and then in the I think 1950s, 1960s, the green LED came along, and so you have red LED and green LED. But if you had, you could make a lot of colors with a red LED and a green LED by mixing different amounts of red and different amounts of green. But if you had red, green, and blue, then you can make all the colors of the rainbow. You can make white light. And so from the 1960s on, there was a big race who would discover the blue LED first. Because whoever discovered the blue LED could make white light.
What do you want to explain that a little bit? What do you mean? Discover? Is it a plan or something? Like they knew what they wanted.
They knew what they wanted, they had to figure out how to make it. Or
Can you explain what like they had to gather materials to make the color blue?
no, they okay.
How do they work? How do LED lights work?
You excite electrons. You excite electrons into higher energy states, and when they eventually come back down, they'll emit light.
Don't you need like a certain type of element to put in there?
Right. Okay, but what element?
There's only a certain, like 127, like 120, maybe it's trying. It's neon? You put neon?
Okay. Physics squad here. My favorite Nobel Prize, the blue LED that lights up the modern world. You know all the LED light bulbs? Those weren't possible unless you had a blue LED. All the LED televisions and LED screens, if you look really close at an LED screen and a TV, you're going to see red, green, and blue. Have you ever looked at that?
Yeah. So we drop a droplet of water on the screen, you'll see the
Yeah, you're going to see red, green, and blue. You don't see the whole rainbow. You just see red, green, and blue, and you mix it. When you go out back at a distance, then you'll see the rainbow colors. But anyway, the blue LED was discovered recently.
Really?
Yeah.
2014.
No, it was before that.
Say what material they use.
That was when the Nobel Prize was awarded.
1980s.
What they use.
I saw 1980 for ground.
This guy's now at UCSB. The guy who discovered the blue LEDs at UCSB.
Was he like
What material did they use?
He was an experimental guy. He wasn't a theoretical guy. What material did he use? I don't remember. It's a ceramic material. He tried lots of different compositions. These are blue LEDs here. In the blue LEDs, they put little material that when excited gives off that blue light. He did all his work in Japan.
And only that material can give you blue LEDs? No other material that can give you blue?
After the initial material, there are lots of materials that give blue, but not enough intensity. You needed both high intensity and blue. And so there were other materials that were giving off blue, but not intense enough for this, you know. And so, this is a very, very long story for this, but anyway, it's just to
Is he
show.
rich now?
What's that?
Is he rich now?
Yes, he's very rich now.
I would assume. Does everyone have to pay
He's
him?
one of the partners of one of these huge light bulb companies.
So are they like the LEDs are like
Should have got a royalty.
Well,
I want a penny from every bulb.
no, the total history is this. He was working for a company when he discovered the blue LED.
They kept the
The company made billions of dollars, and he got like a $20,000 bonus. Yeah.
Well, they were funding him, like he wasn't gonna do it
And you
alone.
couldn't pack.
So what he did was he left that company, but the thing was,
What depends? When does it
the
start?
original iteration of that wasn't very good. He left the company and made even better light bulbs than his original.
Wow,
I mean, they're
expensive.
not
You never actually keep
liable for
anything.
everything, so it's like,
They
well,
thought
that's
they
fine,
had
they
him.
just give me
He was
20
like,
days.
Right.
So if they
Someone's
blow
always
it up,
funding.
then that's on them.
Yeah. Anyway.
Did they have a lot of failures with it? Or
Oh,
once he
yeah.
had it set, they gave him like his bonus, like that's it?
Well, then I guess there's quite a bit of controversy surrounding this. So I don't know the entire story, but
I mean,
He quit,
It
yeah.
makes sense, but it's not fair.
he quit. But the company was thinking that, oh, we already have it, so if he quits, no big deal. But the thing was, it progresses, science progresses, and it continues. So the company made a really, really poor decision, I think.
He
to let it
basically
go,
ruined
but-
the world.
Well, anyway, we got to get back to this. Normally, you follow the procedure, but the thing is, sometimes the procedure is not so good. So we did the chart method, correct?
Yeah.
Copper and nitric acid.
Yeah.
And if we do copper and nitric acid, it looks like a single replacement reaction, but it fails. And so let me tell you some common failures for single replacement reactions.
We write these down.
What's that?
We write these down.
Yeah. All right, one failure for single replacement reactions is the oxidizing acids. Oxidizing versus mineral acids. An example of an oxidizing acid would be nitric acid. I already knew this is going to fail because I'm using an oxidizing acid. And oxidizing acids are a little different than mineral acids. Mineral acids would be like HCl. And so what's the difference between an oxidizing acid and mineral acid? The difference between an oxidizing acid and mineral acid is both are oxidizers. A mineral acid has H plus, like in this case, and Cl minus. H plus is an oxidizing agent. Cl minus is actually a very weak reducing agent. When I look at nitric acid is H plus and nitrate. H plus itself is an oxidizing agent, but nitrate is also an oxidizing agent. So nitrate in combination with H plus is an oxidizer. And so this is different. All mineral acids, the anion doesn't react. And so the reason why this failed is because single replacement makes an assumption. And if that assumption is wrong, single replacement will fail. And so what is the assumption that single replacement makes? Single replacement assumes this: A plus BX. Single replacement assumes that A plus BX yields AX plus B. And so A is the reducing agent, B is the oxidizing agent, X is a spectator. If this assumption is wrong, then single replacement will fail. Well, the reason why it failed here is because nitrate doesn't like to spectate. If we use an oxidizing acid like this, single replacement would predict that H plus would be the oxidizer, that is B. This is our BX. H plus is our oxidizer. That's fine over here. With HCl single replacement, no problem, because H plus should be our oxidizer. But for an oxidizing acid like nitric acid, well, where does nitrate stand? So if we take a look at where nitrate is ranked and compare it to H plus, this is what we're going to see. H plus is here.
Oh, there it is, I see it.
Nitrate is here. Which one's a stronger oxidizer? Nitrate's a much stronger oxidizer than H+. So do you think nitrate's just going to want to spectate and watch H+ take the electrons? No. In this case, nitrate's more powerful than H+, therefore nitrate is going to take the electrons, leaving H+ as the spectator. Well, H+ is not going to be a complete spectator because we need both. We need nitrate and H+ in this, but H+ doesn't get the electrons, nitrate is going to get the electrons.
Oxidize just means that it wants a hydrogen, right? Or-
No.
No, it wants an electron.
It wants an electron.
It wants the electron.
Yeah, a bases want hydrogen.
Basis one.
Yes, you got to drill that in. It's memorizing that. Drill it in. Oxidizers want what?
Electron.
Electrons. But why does an oxidizer want electrons? Why is nitrate an oxidizer? Doesn't it already have an extra electron?
It wants more.
Why does nitrate want more electrons? It's already got an extra electron there.
Wasn't it because it's not nitrate, it's nitric acid? So it's neutral, but we would want more?
Well, it's, in solution, this is strong electrolyte, so the nitrate and the H+ are separate, individual. So why does nitrate want an extra electron? Why is nitrate wanting electrons?
Maybe because N and O are both high electronegative. So together, they're stronger than just. So they're both high. They both have high electronegativity.
Oh.
Not exactly that.
Sure.
N and O are very electronegative, but which one's more electronegative?
Oh.
So O is going to get the electrons at the expense of N.
So
Is
they're-
N going to be happy?
No.
No. How do I know this? Because I remember oxidation states? Tell me the oxidation states.
5.
5 and 6.
Plus 5. Do you think nitrogen's going to be happy losing 5 electrons since it's so electronegative? Oxygen and nitrogen are both electronegative. Nitrogen is essentially going to lose 5 electrons. Is it going to be happy? No. This is why nitrate is such a powerful oxidizer. Nitrate's very dangerous stuff. It's a powerful oxidizer because nitrogen is in the plus 5. Oxygen's happy as is. Oxygen's minus 2. That extra negative charge there comes from one of these oxygens having an extra electron. That's it, but the oxygens are happy at minus 2, but nitrogen's not so happy at plus 5. So nitrate is a powerful oxidizer. What are some other powerful oxidizing acids? Well, nitric acid, nitrate and H+ is nitric acid, right? What's this? Iodate and H+. That's iodic acid. Iodic acid is a powerful oxidizer. What's iodine's oxidation state? No, not this one. Not this one.
Oh.
IO3 minus
Plus 5.
plus 5. Iodine is not happy plus 5.
Why isn't it happy being plus 5? Oh, wait, never mind.
It wants to be minus 1. Dichromate and H+ makes dichromic acid. Is dichromic acid happy? No, dichromic acid is unhappy because of chromium. What's chromium?
5. Right there it's
Where is C?
6. It would be 6. That might be the weird one. I think it started plus 2 plus 3.
Isn't it plus 2 plus 3?
No.
It's different. That's the charge. Is it plus 6?
6.
Plus 6.
Yeah.
Plus 6.
And in this case, it would be minus 2.
Because 07, that's 14.
12.
What do you think about this acid? Is this a mineral acid or an oxidizing acid? Is that a mineral acid or an oxidizing acid?
What was it?
Oxidizing acid, Jose? Yeah.
Well, it depends. It would depend on ClO4, right? The ClO4.
Yeah, well, tell me what it is. Look at the oxidation states and tell me.
How do you look at oxidation?
Oh yeah. So the Cl would be not happy, right?
C.
Yes.
Oh,
ClO4 alone.
It's just supposed to assume that's like
We're
H.
comparing. Is ClO4 minus going to be a spectator in redox, or is it going to react?
It's gonna react.
It's going to react. Why is it going to react?
Because of the oxygen. Oh, because of the CL is gonna be unhappy.
Cl is going to be unhappy because why?
Because it doesn't.
It's
because
plus
at
7.
It's +7.
And it wants to be -1.
Yeah.
So it's giving me in a lot more than it should.
I was thinking because you said H is supposed to be
So-
the oxidation and then everything. else.
Yeah, so if you compare perchloric acid with nitric acid, which one's worse? Which one's more dangerous?
Perchloric?
Perchloric by far. Is perchloric on this chart?
No.
No, perchloric's not on this chart, but this is why we want a two-pronged approach. We don't want to just memorize this chart because that's not enough. What we want to do is we want to understand things a little bit theoretically. So here's a little bit of theory. We talked about oxidation states. We could figure out. We didn't need to be told that perchloric. This is two answers come up with this. Answer number 1, hey, that's not a fair question. Perchloric acid's not on this chart. That's not fair. You shouldn't ask us that question. You know, then I know, okay. And then answer number 2, somebody figured it out. Hey, perchloric acid, that's going to be one nasty oxidizing acid.
So what makes it nasty? Because the Cl is +7, but you said it wants to be -1.
Yeah.
So, but you said oxidizers
Oxidizes one
want
electron.
electrons.
Right.
So to get -1,
Yeah, you
so it
have to-
wants
It has to take
To
a
go
lot.
from +7 to -1 requires 8 electrons.
So the more it requires to get to
To make it happy, then it's
Yeah.
so that one's stronger because it's +7. So it needs a lot more electrons in.
Right. Well, what do you think wants negative charge more? +7 or +5?
+7.
Yeah, but we can't always go by that because it also depends on the element, you know. So
And what happens if it got to minus? Then it would separate
no, it might not get all the way there. You know, it might just go to 0. Take a look what happened to iodine. What does iodine want? Iodine wants to go to -1. Did it make it all the way there? No. It just, it went to 0. So here it went from +5 to 0. Well, that's still pretty good because that means each iodine gained 5 electrons. So it's still pretty good. Each iodine gained 5 electrons. There's 2 iodines, so it's going to gain a total of 10 electrons. Does that make sense?
What's the oxidation state of iodine?
0. But you know, some of these are already 0, like chlorine. Chlorine's 0. Why does it want electrons? Because chlorine doesn't want to be 0. Chlorine wants to be -1.
Oh, so in IO3 it wants to be -1.
Well, or at least closer to -1, even if it doesn't get there, -1. Like nitrate doesn't make it. Nitrate would like to go to -3, but nitrate only makes it to. Nitrate goes from +5 to no.
0?
No?
Oh, +2.
+2.
So it gained 3.
So it went from +5 to +2, so it only gained 3
Oh,
electrons.
that's where the electrons. So the electrons in the middle help you a little bit.
Yeah. Yeah, so we could see what happened. Well, that's better than being +5. Being +2 is better than being +5, so that's what's going to happen there.
Yeah, so O is -2, so balance it out is neutral. Yes.
So if you're dealing with you have 2 choices here. One, you could continue using single replacement and just memorize all the exceptions. And so the first exception to memorize is that single replacement does not work with oxidizing acids. That's the first one. Okay, the next exception is this. Single replacement does not work with halogens. So for example, if I had this reaction, between bromine.
Do you ever put fluoride and stuff?
I'm sorry?
Have you ever put like fluoride and stuff?
Yeah?
Does it take all the electrons?
Does it what?
Does it take all the electrons?
Fluoride? No.
Yeah.
Fluoride takes no electrons.
Wouldn't it be the most electronegative?
Fluoride is the most happiest species on this list.
That's all.
Fluoride is the most happiest, least reactive species on this list.
F alone would
Because fluorine wants to be -1 and it is -1, so it's happy as is.
It's -1.
Yeah, fluoride is -1. What's chloride?
Oh, -1.
-1. Iodide is,
-1.
yeah. And so sodium iodide,
it's neutral.
Yeah.
sodium is +1, iodide is -. Well, what forms here? Well, we should form bromine iodide plus sodium solid.
Well, that's one of the ones that came up on the book.
I'm sorry?
I think that's one of the ones that came up on the book where the I, they switched it out and made I by itself.
Yeah, so for halogens, we can't use the single replacement. This fails. So we have to use a different pattern. The pattern we use for halogens is x2 plus AY. 2AY yields 2AX plus Y2.
So whenever it's a halogen, like the equation for the most part is going to be like that, like the x2.
Yeah. So you have a choice. You can memorize the single replacement pattern for halogens or just use the chart method. In the previous example, when you have an oxidizing acid, you can only use the chart method. There's no other simple pattern for that. All right, the third failure of single replacement is when water reacts. And so an example of this would be like this. So if we take potassium and sodium chloride, what should we form? We should form potassium chloride and sodium solid. If we go to look at the activity series, potassium turns out to be more active, less stable. Sodium is less active, more stable. So there's driving force, yeah. Driving force. But this is totally wrong. And you'd have to know this. Well, one clue, this is totally wrong. Even though the driving force is there, even though this works, it's wrong. It's the wrong reaction. Why? Well, a couple of clues. One clue here is this. What is special about potassium? Is anything special about potassium metal?
Well, it's a metal, so it should be it's a alkaline.
Well, if you know this chart, then you know what is the strongest, most powerful reducer on this chart? Lithium. And then potassium. So one of the things you recognize is potassium is very powerful, which means it's very reactive. What is the oxidizer in this case? The oxidizer is sodium ion. Is sodium ion very reactive? No, sodium ion, calcium ion, potassium ion, lithium ion, these are all very stable. Remember, the conjugate relationship is this. If these are very reactive, its conjugate is very stable, unreactive. And so a couple of clues that we might be dealing with something a little more in this particular reaction is because of potassium. And so when we're dealing with very powerful oxidizers or very powerful reducers, you probably don't want to put it into a simple pattern like this. You probably want to use the chart method, which is better. And so let's use the chart method to figure out what this is. Now the chart method, we just follow the steps. What's the first step in the chart method?
Inventory.
Yeah. And so we'll inventory. So we've got potassium solid. Can I write this as K plus? Are potassium ion and potassium metal the same thing? No. And so which one do I have? Do I have potassium ion or potassium metal? Potassium metal. If I have potassium ion, that's a whole different story. Potassium ion is stable, really unreactive. And I have sodium ions. Sodium ions are pretty stable. They're unreactive. I mean, when you salt your French fries, are you worried about some violent reaction occurring?
No.
Maybe with your stomach you might have a violent reaction if there's too much salt, but other than that, no. Chloride, not very reactive. And then what else is present here? Water.
That's just because.
It's all the same.
Hey, but isn't water the worst? Is water the worst? Isn't it the worst oxidizer on the chart?
No, it's between
No. Water is actually between what?
the nitrate and HEC.
No.
Oh, that's
Water is between what?
Zinc.
Zinc and aluminum. Good. It's right here. That's where water belongs. So what that means is water is a stronger oxidizer than all these, but a weaker oxidizer than anything above it. Okay. So what that means is this. Okay, this is the next level of understanding the chart. You can understand the chart to predict reactions. So for example, if water is here, well, let me do another example first. Iron 2, oxidizer or reducer? Oxidizer. And so if iron 2 reacts with zinc, let's say iron 2 reacts with zinc, zinc goes from zinc metal to Zn2 plus. So iron 2 reacts with zinc, we form Zn2 plus. Are we going from a stronger oxidizer to a weaker oxidizer, or a weaker oxidizer to a stronger oxidizer?
No, we're going from stronger
Stronger
oxidizer to
oxidizer.
weaker
Yeah,
oxidizer.
stronger to weaker. Do you see that?
Yeah.
Okay, so that what that means is iron 2 will react with any of these down here. Because if iron 2 reacts with aluminum, we'll form aluminum 3 plus, weaker. If iron 2 reacts with magnesium, we'll form magnesium 2 plus, weaker. If iron 2 reacts with soot, do you see that? The
Yeah.
pattern? But what if iron 2 reacts with tin? If iron 2 reacts with tin, we form tin 2, which is a stronger, so we're going from weaker to stronger. Is that favorable?
No.
No. So what this means is iron 2 reacts with zinc, aluminum, magnesium, sodium, calcium, potassium, and lithium. It reacts with all theirs.
Reacts with.
Right. And so what that means is that water is here between zinc and aluminum.
So it will react.
And so water will react with aluminum, magnesium, sodium, calcium, potassium, and lithium. So we have to be careful when we have water and something this powerful. And so we don't have to know that. We just go through the steps. What's the next step here in the chart method?
Finding
Acid,
or
identify some.
oxidizer.
Okay, so we got to label these. Potassium is a reducing agent. Sodium is a
Is it neutral?
sodium ion is a
Oxidized?
oxidizing agent. Chloride is reducing agent. Water is both. And so the first step is we got to figure out what the strongest oxidizer is. Sodium ion versus water.
Probably sodium. You said water was the weakest, didn't you? You said water was the weakest?
I said water is the weakest because lots of people think it's the weakest because it's at the bottom of the chart, but you're the one who told me it's not at the bottom of the chart. Water is up here, which means water is a stronger oxidizer than aluminum, magnesium, sodium, calcium, potassium, and lithium ions. So is water a stronger oxidizer than potassium ions, or potassium ions is stronger than water? Which one's stronger? Water. So right now, the single replacement fails because single replacement is going to assign the role of oxidizer to sodium. That's wrong. Sodium's not the oxidizer. Who's the oxidizer? Water. If a reaction occurs, we got to see if there's a driving force. Yeah, potassium metal is a stronger reducing agent than
Where is Cl?
chloride. And so, where's Cl minus? It's way up there. Here's potassium metal, second strongest. Where's Cl minus? Near the top.
So it's a weaker reducing agent.
Yeah.
The right side
Okay, what's the next step?
Seeing if they react.
Well, the next step is combine the strongest oxidizer half reaction with the strongest reducer half reaction. So what that means is this.
Oh, you write the K or you put
Right.
K plus E or is it K?
Is it K plus E, or is it?
I think it's K, then equals.
Yeah, it's not this. It's not this because we don't have K plus. We have K. So I have to reverse it. It's going to be K solid goes to K plus electron. I have to reverse this because I don't have any potassium ion as a reactant. I have potassium metal as a reactant. So I've got to flip this so that potassium metal becomes the reactant on the left and potassium ion plus the electron becomes the product on the right.
And then it'll be.
So again, I cannot use this equation because I don't have potassium ion, I have potassium metal.
And then you do 2H2O plus 2E.
Yeah.
To equal H2 gas plus 2OH.
Right. And so the other equation is going to be this one. 2H2O plus 2 electrons yields H2 gas plus 2 hydroxides. Then I have to make the electrons equal on both sides. So I have 2 electrons on the left and 1 electron on the right. How can I make them equal? Multiply the bottom one by 2. And so now what I see is that the 2 electrons on the left side cancel out the 2 electrons on the right side, and then I can just add them up.
2H2O plus 2K. Or would you put 2K?
Yes.
2H2O.
So I'm going to do this here. I'm going to add up everything on the left. 2 H2O liquids. The electrons I cancel out, plus 2 K solids goes to H2 gas, 2 K plus 2 hydroxides. It doesn't matter which way. No, aqueous.
Is it always aqueous?
And then the driving force
Yeah.
is.
Well, the driving force, the easiest place to do the driving force is from the half, these are called half reactions. What was water again? Water is and so we use the conjugate relationship. If that's the oxidizing agent, this will be the conjugate reducing agent. Potassium is reducing agent. If that's the reducing agent, the potassium ion must be its conjugate oxidizing agent.
So.
And so we'll use this to figure it out. This is our OA. This is our RA. Now hydrogen and hydroxide, I should have split them up, is our RA, and potassium ion is our OA. All right, we still don't know if a reaction is going to occur. We have to figure out the driving force in order to determine a reaction occurs or not. And so let's compare the 2 oxidizing agents. Yeah. Water is between zinc and aluminum. So water's here, potassium ion's here. Which one's stronger? Water. So we're going from stronger oxidizer to weaker oxidizer, potassium ions.
The same rule will be for the reaction.
Yeah, because of the conjugate relationship, the same, it has to be the same. This has got to be stronger, this has got to be weaker. We can confirm that here. Potassium metal is stronger than, where's hydrogen and hydroxide? Oh, down here. Hydrogen and hydroxide, but it doesn't belong down here, it belongs up there. Right? Between zinc and aluminum. Hydrogen and hydroxide. And so we have driving force for this particular reaction. All right, any questions on this?
Wait, the driving force is from the strong oxidizer to the
Stronger to weaker. It doesn't have to be strong, just stronger.
And both strongs have to be on the same side?
Yes. If both strongs have to be on the same side, if not, you did it wrong.
It's from the opposite side of the thing, right? It's from like on the arrow side, so where you know where it lands on the outside spectrum.
On the for the chloride, we look here. Chloride only occurs on one side on this chart. Chloride occurs on the right side, so we have to compare with lithium down here. Lithium's the strongest, so chloride's a reducing agent. And so if chloride reacts, then we would have to flip the equation over, but it doesn't react in this particular.
But like, how would you compare its strength to the other side on the bottom?
We can't compare it. We can't compare it. This is like, okay, what's the biggest? Oh, let me tell you the biggest orange. The biggest orange is fluorine, and the biggest apple is lithium. The biggest orange is fluorine. The biggest apple is lithium. Okay. Yeah,
That's
you
like
can.
one of
And so
lithium.
therefore, chloride is an apple. We can't compare it to the orange side because it's an apple. And so we don't compare it to anything on the opposite side.
Wait, which one was the most violent reaction again? We saw the video of it. It was with fluorine and
So
So,
with the one with the kid was touching with her name.
all right.
That was sodium and water.
Yeah.
This is why I say, you know,
That ended up blowing up the time.
this one has no reaction, right? But in single replacement, this would be a no reaction.
Yeah.
But we could see, you know, this. You want to see this reaction?
Yes.
We'll take a look at this reaction.
What's the most dangerous reaction you've done? Wasn't that one?
Probably ones that cause explosion.
I know, but what's like the most dangerous?
Well, the most dangerous that can be done on our chart
No, like
Yeah.
you've done, like from your experience.
that I've done
Yeah.
just the all.
a lot. I've done I've done some that weren't. I mean, I've done this.
You've done this.
You said it's hand on fire?
I've done this a bunch of times.
Is it sodium already?
Well, that's the thing that you told us about.
This is sodium and water. Yeah, this is the kid touching it. Did you see that explosion?
Yeah.
Can you imagine like poking your head over that right when that goes off? That was kind of a delayed reaction. Let's take that. Let's take a look at that reaction.
All
one more
that
time.
heat and steam will probably smell your face.
Did the beaker break?
It can't. I've cracked beakers before. That's not good. All right. Take a look. This is sodium in water.
Wait, that
Boom.
sodium bullets like in the water.
All right. That's sodium in water, slow-mo. Watch potassium in water. Is potassium more violent or less violent? Well, we'll see. This is potassium metal.
Oh, gosh.
You see, there was no delay there. It went off immediately. Watch this again. Boom, right there.
Oh, and that's like, there's gonna be like a bigger explosion.
In our bodies.
So potassium, well, that was a tiny bit of potassium. You know, I already told you, did I tell you that we had some extra potassium in the laboratory that needed to be gotten rid of? There's about a kilogram's worth of potassium that was thrown into the faculty pool at UCSB
Oh,
that created like a 40-foot, like just a 40-foot, just
Wait, the water?
wave of water.
That's the only way you can
Yeah,
dispose
and
of
a
it?
huge bank. What's that?
That's the only way they can dispose of it, put it in water?
No, you could dispose. I used to dispose of it much more gently. I used to dispose of it in alcohol, but one of the things about disposing of it in alcohol is alcohol is very flammable, and so
Yeah.
it could lead to a nasty fire potentially. But hydrogen is very flammable too. But I don't. The potassium that wasn't that bad.
Just casually touching it.
I have a question. What kind of potassium do we put in our bodies? Like, is that potassium ion?
like rinse some water.
Like
Yeah.
potassium pills?
Like you need potassium in your diet. Like people eat bananas to get potassium. But are they getting potassium metal or potassium ion from the bananas?
That's why, what's inside the pill then?
They're getting potassium ion. They're not getting potassium metal.
And that's not gonna explode in them?
That's not going to explode in them. Potassium ion is
That'll be crazy. If you eat a banana and you drink a water bottle.
Well, you tell me, is potassium ion very reactive?
Not as an oxidizer.
No.
As an oxidizer, it is an oxidizer. Is it very reactive?
No.
No, it's all the way on the left.
Potassium ion is very unreactive. It's very stable. So we don't worry about it. It's the second worst oxidizer on the chart. This is why you have to worry about redox there. All right, we'll take a break now and then we'll finish up redox after that.